Okay, so day 3. I'm recording, guys. You need to keep it down. All right. So yesterday, well, 2 days ago, we covered all the math that we need to worry about. Yesterday, we covered classification of matter and separation techniques. Those are the things that are on tomorrow's quiz. Okay. Nomenclature and laws of multiple proportions won't be on this quiz tomorrow. It'll be on the following quiz. If you're looking at me like, we have a quiz, where do you find that information? On your calendars. All right. So law of multiple proportion, it's going to be seemingly confusing, but it's really not, and it's a really simple law. I'm only covering it briefly because it is part of the redesigned, it's in our course description, have yet to show up on the AP since it's been redesigned at all, but it's kind of a common sense kind of law, and it basically says that when you have compounds that are made, they are all small, they can all be derived down to a small whole number ratio or small whole number multiples. Like, we do empirical formulas, kind of a similar idea, but instead of doing moles here, they're doing it from a mass perspective. So for this problem here, we're going to illustrate the fact that we do have a small whole number ratios that exist when nitrogen, these are all these grams here represent grams of the nitrogen as they react with just 1 gram of oxygen. Okay? So think back to empirical formulas. We had moles of all these different elements, and you're supposed to figure out the smallest whole number ratio. What did you do? You had all the moles, and what did you do to find the smallest whole number ratio? Divide by the smallest, exactly. You went and divided by the smallest. So we're going to take, in all these compounds, the amount of nitrogen that's present in all of them and divide all of them by, of the information given, the one with the smallest amount of nitrogen. And if this data is correct, we're going to see there are whole number ratios of those relationships. So we're going to have compound A has 1.50 grams of nitrogen. This has 0.875. So we're looking for the smallest multiple. Okay, so we can divide all of these. What's the smallest number of grams in our examples? 0.4375. Okay? What did I do? Sorry. All right, thank you. All right, so we're going to take all of those and do the division. And when you do that, you get a 4 here, and you get a 2 there, and you get a 1 there. Right? So what is that telling us? What that is telling us is that A has 4 times as many nitrogen atoms as C does, or 4 times the amount of nitrogen mass as C does. This says that A has 2 times the amount of nitrogen as B does. The fact that these are whole numbers is supporting the law of multiple proportions. Where this comes into play is in these pictures. And I don't want you to freak out about this. Again, this is very lightly covered. Remember, our ratio was 4:1. These are all representations of the same 4:1 ratio with nitrogens with respect to each other. So just looking at A, you see how this is a times 2, like we said, that A has twice as many as B does. Okay? Now this one, don't let it confuse you. Even though we're supposed to have a 4 times as many atoms, they doubled the O's, which took care of that. Because if you look at this ratio, a 1:2 nitrogen to oxygen ratio, when you multiply it by 4, what do you get? 2. Isn't this a ratio of 2? Okay, so this is just a play of proportions and a play of numbers, and it's not something to stress out about. If you kind of get it, that's good enough. And if you're good at math, this should be actually pretty easy. So this is just taking it a bit further using those same ratios to get all sorts of different combinations of nitrogens to oxygens. But they're all based on that 4 to 2 to 1 ratio. So on the homework, number 3 tonight, I'm basically going to tell you how to do it, sort of. They give you, and it turns out to be the exact same problem we're looking at here. They give you 3 compounds again, but this time they're giving you percents. They're saying that, hey, all these compounds only have nitrogen in it and oxygen in it. For A, we have 63.65% of nitrogen. They don't tell us the percent of oxygen, but can we figure it out? How? Subtract from 100. So when we do 100% minus that guy, we get 36.35% of O. Now, we really can't do a proportional thing here because what made this problem special on this last thing was the fact that we were holding this at a constant 1 gram of oxygen. And so everything was based off of that. So to do this problem in your homework, we're going to have to do a proportion and figure out, okay, how many grams do we actually have if we only had 1 gram of oxygen. So what I'm going to do, remember in empirical formulas, we just pretended those are grams? Yeah? So what I'm going to do is I'm going to set up a proportion. 63.65 grams of nitrogen is to 36.35 as what is to 1 gram. And we're going to convert all of these to a 1 gram oxygen ratio. If you do it right, which you will, you're going to get exactly these numbers. That's where the numbers came from. So if you just do that first one, you can see you get 1.75 as the number that gets you to 1. So then what do? You do the same thing we did. We take all of these, divide by the smallest, and we get that same 4 to 2 to 1 ratio. So someone said, well, how does that answer the question? Well, the question is answered by the fact you got whole numbers when you did the work. And that proves it's multiple proportions. Okay? For number 4 on the homework, basically what they're saying is, this is like a Millikan oil drop kind of experiment. You guys did that. Did we do that last year with the marbles and the boxes? No, I don't think we did that last year. Anywho, what's going on here is they're giving us the charge of all the electrons summed up, and you're supposed to find a common multiple for all of them. It's actually really, really, really easy. And so what would be the first thing you might want to try to do? Divide by the smallest. I heard Jake say that. Turns out when you do that, you get whole numbers. So what the charge of 1 electron would be what? What that smallest value is, the thing you divided by. So that's how you do number 4, okay? All right, I usually don't go over homework problems in that detail. I just find those to be a little confusing. So I wanted to make sure you were going to be okay with that. So now we're going to go totally switch gears and go into the land of the periodic table, the parts of the periodic table, and nomenclature. We're going to do binary nomenclature today. So let's review the parts of the periodic table. I need you to know the names of the groups and families. So group 1 is known as the alkali metals. It doesn't include hydrogen. Based on number of valence electrons, hydrogen is located here. Based on the fact it's a nonmetal, it's kind of also located there. So just know it kind of does both things. So it's not considered a metal, but the rest of these guys are alkali metals. Group 2 is known as alkali earth metals. All of these guys are known as transition metals. And then we know that we have the halogens here. Hydrogen's not considered a halogen. Halogens here, and what's this last group? Noble gases. Okay? And then down here, these guys, which are inserted in the transition, are known as intertransition metals or rare earth metals. Either one is fine. Who remembers this business? What did that line stand for? Well, I think I messed it up. Anyway, these things right here are known as metalloids. We're in AP Chem, I'm not going to sit there and make you pick out, is this a metalloid, a metal, or a non-metal? We don't do that. That's well above our pay grade, well below our pay grade. We're going to be working on other stuff. So don't sit there and stress too much on, that's on the line, is it? Aluminum's a metal, and it never acts as a non-metal, but it's kind of sitting on that line, so that's what I'm saying. Don't worry too much about it. Okay? What else about this? I think that's all for this slide. Now, if we look up at this big periodic table, and even on this one, you have these numbers. What were those? Atomic number, and what did they tell us? It's known with a, it was indicated with a Z, atomic number. What does that tell you? Number of protons. The number of protons tell the identity of the substance. So we can't be changing numbers of protons when we have charges. We only change numbers of electrons when we have charged species. Okay? And then underneath it on the periodic table, you've got these numbers that have decimal places. So like oxygen, you have 15.994 written right here. What is that? Atomic mass. But aren't protons and neutrons like 1 AMU each? So why are they decimals? You can't have a 0.5 of a proton. It's an average of the isotopes. Well done. Yes. So because it's an average of carbon-12, carbon-11, carbon-13 at different percent abundances, we report the atomic mass with a decimal. So I prefer if I heard you say average atomic mass, because that's really what it is. Okay? We're going to be doing calculations of average atomic mass fairly quickly here. It's one of those review topics we're going to hit in the next couple days. So here we have something called condensed formulas, where you're expected to be able to do these and interpret these. So whenever you have it, you have the element. On the bottom is the atomic number. What's this called, like this 109? Mass number. Mass number usually indicated with an A. Sometimes people just, anyway. So mass number tells you what? Protons plus neutrons. Why isn't it a decimal this time? Not the most common. No. It's what that specific atom has, right? So there's going to be other silvers that have different atomic numbers, but this guy right here has an atomic, not atomic numbers, mass numbers. This guy right here is this, its own isotope. It's going to have its own mass of protons and neutrons, okay? So in order to do these problems, you have to have mass number. Now, I've heard of some people, and last year when I was teaching pre-AP, were saying, oh, they'd have you round that number up there and subtract to get neutrons or something. No, you can't do that. You have to be given the specific isotope in order to find exactly how many neutrons. I also heard that some of you learned that you have the same number of neutrons as protons. No, definitely no. So erase all that from your head. In order to figure out neutrons, you have to know what isotope you're dealing with, okay? So what we're going to do, I like doing protons, neutrons, and electrons like this because I'm lazy and I don't want to rewrite stuff. I don't want to write the word proton 4 times. Okay, so let's do that silver one first. How many protons? 47. Neutrons, how many? Where'd you get that? Subtract 47 from the 109 because that 109 is protons plus neutrons. Now we do electrons last because we need to look at it in terms of charge. So we got to know how many number of protons that are in existence. So silver atom has no charge. So it's going to have the same number of electrons as protons. So when you're changing if you have something that's charged, you add or subtract from the electrons. Do not touch the protons because it changes the identity. Okay? That's really important. And neutrons themselves are what charge? No, they're neutral, and then electrons are -1. And physics gets really mad at us all the time about, we have a friendly rivalry. So they're all like, the charge is not 1. Da, da, da. We're not defining charge with the units of what's a charge unit. Who's taken physics before? Coulombs, right? We're not defining this as 1 coulomb. No, it's not 1 coulomb. Of course not. We define our charge in senses of AMUs, atomic mass units. So it is 1 atomic mass unit of charge. So when they say we're lying, we're not lying. We're defining it appropriately. We just define it differently. So tell them to just be quiet. So, because they will get to that, and they're going to totally stomp on chemistry, because that's what they do. And I stomp back. So anyway, so a neutron walks into a bar and says, hey, bartender, how much for a beer? And the bartender says, for you, no charge. My pre-APers remember that from last year. Get it? Great. It's awesome, and the neutron is 21. So he's allowed to walk into a bar. Good decisions. Thank you. Okay. Magnesium, how many protons? 12. How many neutrons? 12. And then electrons, there's no charge on that, so 12. Aluminum, 13. Good. All right, we have something with a +1. We're going to keep this as 47. That's its identity. How many neutrons? 60. Now, in order to have a +1, we need 1 more proton than electron. So what do we write for electrons? 46. Okay. All right, let's just do a -1 just in case some of you are struggling. Let's do a just add sulfur 32. How many protons? How many neutrons? Now, how many electrons? 18. So I want to make sure y'all know that. Don't be surprised if on your test you get something with like a +500 charge. Don't, just, I'm testing if you know how to do it, not if you just guess based on the fact you know certain things. So anyway, moving on. Any questions on this? All right. So what we need to do to start naming compounds is to identify the different charges that exist in our ionic compounds. All right? Ionic compounds were composed of what 2 elements, types? Yes, metal plus nonmetal. So the way we put these together in naming is by balancing the charges. Okay? So you need to know what the charges are. So the best way to do this is go back to that periodic table, and we're going to I'm going to add in there, I'd like to change the color of my pen, see if I can do it. I think I just did. Awesome. Okay, so looking at this, we know that all of these guys right here are what? What charge in an ionic compound? +1. Group 2 is +2. Okay, transition metals, all but a few of them are multivalent. They have more than 1 charge. So usually you'll just be able to figure that out based on a Roman numeral you're given or based on a formula. But there's a few I want you to memorize, which we'll get to when we get to multivalent. So let's just go on to this nonmetal side. Arsenic can go either way because it's metalloid. I want to focus on these 2, nitrogen and phosphorus, that when they are acting in not in a covalent compound with oxidation states, I'm saying when they are charged in an ionic compound, what is their charge? Okay, yeah, this is not rhetorical. Thank you. I was beginning to get worried that y'all didn't remember nitrogen and phosphorus for -3. All right, what about oxygen and sulfur? -2, and then all the halogens are -1. And then noble gases, they don't ionically bond with anything. Everything above level 3 that can kind of expand their valence, which we'll talk about, these level that we argon, these guys can bond, but they only do it covalently, so there's no charge involvement. We can get oxidation states, but not charges. Okay, so now let's talk about your next question. Oh no, we have some univalents left. Does anyone remember which transition metals only had one charge? Silver. Silver was +1. It's a stair-step thing. Oh, I forgot aluminum. Aluminum is always +3, and that helps because now we have our stair-step. 3, 2, 1. There's a stair-step there. 3, 2, 1. Yeah. That was the next thing I was going to say. Cadmium is going to be +2 because these two are together. 3, 2, 1. Those are our only univalent transition metals. Now, if you took regular chemistry, you didn't have to memorize what I'm about to tell you, but guess what? You get to learn it now. The rest of you in pre-AP, we did this, so it's just a matter of remembering. Iron, cobalt, nickel can have 2 charges, and it's good for you to know because it helps when you're doing nomenclature and certain things. Plus, reaction prediction, you'll need to know what those charges are. What are the 2 possible charges? Who remembers? +2 and 3. +2, +3. Iron, cobalt, nickel are +2 or +3. I'm not going to do all of the transition metals. That would be crazy. Copper is +1, +2. Copper is +1 and +2. Iron, cobalt, nickel is 2, 3. Copper is +1, +2. Au, this is gold. Get it? Au. Oh man, y'all are dry. You are very critical. I'm going to bring in like some famous comedian one day and maybe you'll actually laugh. All right, does anyone remember gold? +1, +3. +1, +3. Mercury's kind of special. It carries a +1 or a +2 charge, but does anyone remember an issue with that? Exactly. In order to have mercury +1, you can't have that. That doesn't exist. It exists as that. That's mercury +1. And mercury +2 just looks like this. So there's a difference there. Do you see the difference between these two? Yeah? There's a difference. This is a +1. Each of the atoms has +1. This is one atom with a +2. Okay, and the last little bit here, tin and lead and antimony and bismuth. I like looking at them together because it's kind of a pattern. Who remembers that? 2, 4, 3, 5. 2, 4, 3, 5. 2, 4, 3, 5. So if you were to write down a list for me and say, tell me all the divalent charges, I need a periodic table because I don't remember which one's which unless I see it in pattern, and that's how I learned it. You'll always have a periodic table, so you'll be fine. No, these two are 2, 4. These two are 3, 5. Divalents, they can be those 2 charges, and only everything we've been doing. These can be 2 or 3. This can be 1 or 2. That can be 1 or 3. That could be 1 or 2. 2, 4, 3, 5. Okay. Now, when you're naming this stuff, and you're naming these transition metals, even the ones we didn't just go over, you have to indicate with the Roman numeral what the charge is. And usually there's clues within the compound that'll help you figure that out. So let's pop into the world of nomenclature. Now, you don't have this flowchart on your paper, but it's in your textbook, and I'm just going to go over it really quickly. Today, we're only naming things with 2 types of elements in it, binary nomenclature. So we're either going to name nonmetals put together or a metal and a nonmetal put together in different proportions. All right? So ionic compounds versus covalent. All of these, notice, have metals. So these are all ionic compounds. You're not going to always have them nice and separated. You're going to have to remember how to name them when they're mixed up. So if you look at this flow chart, which you can't see very well. In the video it'll be very clear, but here it's not. So if it's a binary compound, is it? Yes. Are there metals present? Yes. The ones we're looking at right now are. The question you have to ask, is the metal univalent or does it have more than one charge? If it's univalent, one of the ones that we wrote is only one charge, you just name what you see. No Roman numerals are allowed. Okay? If it has more than one charge, you have to put in that Roman numeral, indicating what charge it is. So let's go through. Number 11, what is that one? Sodium chloride. Sodium has only one charge because it's the group 1. So we don't have to put in a Roman numeral. Going over to the right, does calcium have more than one charge? Nope. So we just name what we see. So what is this called? Calcium. Why didn't I say dibromide? It's not covalent. What's taking care? What's giving us a 2 though? We're not saying it's dibromide, but what's making it 2 be ours? The charge. Because there's only one combination possibility of calcium bromide. That's only one way to do it and make it neutral. Now when you look at covalent compounds, you can put them together in all different ways. You can have carbon monoxide, carbon dioxide, nitrogen trioxide, nitrogen monoxide. So there's not that same issue. That's why you have to have the prefixes. Here this is based on charge balance. Only one way to do it. Okay? What about K2S? Does potassium have more than one charge? No. So what's the name of this guy? Potassium sulfide is correct. Now notice they're all ending in IDE. Any binary compound, the ones we're doing today, are going to end in IDE because these don't have polyatomics in them. Once you start adding in polyatomics, the name will be based on whether it's a nitrate or a nitrite, based on the combination in that polyatomic. So everything today comes off the periodic table straight up, so it's IDE. All right, we got copper. Does copper have more than one oxidation state? Yes. So copper and nitrogen. So I can see this very quickly. If you can't, let me just show you the gist of what's going on. Because this has more than one charge, we're going to need a Roman numeral. So nitrogen normally is what charge? -3. So -3 times 2 means this side of the molecule is -6. So this side has to be a +6, but I've got 3 of them. So what is each one? Copper is +2. So remember, we said copper could be 2 or 3, so we're on the right track. If you do a problem and you get a copper 7, no, it can't happen, all right? So all the answers have to make sense. So this is a copper 2. So you're going to write copper, and then you're going to do Roman numeral 2, and then you're going to write nitride. You do not need to even look up at the periodic table when you're determining Roman numerals or when a Roman numeral is given to you, because that's what this is doing. This is telling you what that charge is. Now, if you need the charge of nitrogen or something, yeah, you'll need to look it up, but they're giving you the formula here. They're giving you the ratio. Okay, AlF3. Does aluminum have more than one charge? Nope. So what is this called? Aluminum fluoride. Ag, silver. Does it have more than one charge? No, it doesn't. So let's see if y'all can handle selenium. Aluminum selenide. Not aluminum, sorry. Silver selenide. Selenide. I had aluminum on the brain. Not literally. That would be bad. Okay. We have a cobalt. Does cobalt have more than one possible oxidation state? Yes. It's attached to 3 iodines. So what's its oxidation state? Cobalt +3. So we're going to put a 3 in parentheses. Now, you're not going to get sympathy from me this year with sometimes I'd let it slide if you had silver and you wrote silver 1. I was like, oh, okay, whatever. Not this year. If it only has one oxidation state or one charge, you are not to put down these Roman numerals. Okay, it's only when they have multiple ones. I can't let that slide this year. All right, SN, what does that stand for? 10, and it's attached to 2 sulfurs, so what's its charge? 10-4, good buddy. 10-4 sulfide. Okay? All right, now we're going to go in the reverse direction. And again, these are kind of separated, so don't get used to it. These are all metals. Metal, 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 metal. So we're going to have to balance charge to write the formula for these. So calcium is what charge? +2. Sulfur is -2. So what's the formula? CAS. We're going to fly through these. Barium is, thanks, I meant the charge, sorry. Barium's +2. Fluoride is -1. So what's the formula? BAF2. Cesium is +1. All right, hydrogen. Hydrogen, like I said, is a weird beast. It'll be positive, it'll be negative, it'll do different things. When you see hydride, it's acting as a nonmetal, and that's what it's going to be. So if it's a hydride, what would the formula be? CSH. Lithium phosphide. Lithium is, phosphide is -3, so it's Li3P. Copper 1 oxide. It is telling us what copper is. So you have to, don't worry about it. You don't need to look at the periodic table. It's telling you copper is +1. Oxygen is -2. So what's the formula? Cu2O. Same thing with this one. It's telling you bismuth is a +5. Sulfur -2. Oh, that's a big one. What is it? Correct. Nickel 3 bromide. They're telling you nickel is a +3. Bromide's a -1, right? It's a halogen. So what's the formula? Br3. Cadmium. They don't have a Roman numeral there, so they're telling you, hey, that only has 1 charge. So what is cadmium's 1 charge? +2, and this is a -3, so what is it? Correct, CD3N2. Okay, so those are ionic namings. So our boys in the back, every time I turn around, you guys are talking, I turn back and you stop. And I turn around and you're talking, I turn back and you stop. All right, so looking at this, these are obviously covalent compounds, okay? They are all nonmetals, so we're going to use our prefixes. We need to remember what those prefixes are. I need you guys to know 1 through 10. When you get to organic, we get to up that number. All right, number 1. How many for one thing? What's our prefix? Mono, 2. Di, 3. 4. Tetra, 5, 6, 7, not septa, septa's geometry, 8, octa, 9, 10, deca. Now, I'm not going to freak out if you leave off a vowel or something, because sometimes you get things like triiodide, and you might not realize there's 2 I's in there. I'm not going to like flip out and mark it wrong or anything like that. So don't stress about it, just try. Same thing like oxide. Students have a really hard time putting 2 vowels together, but it happens. But if you don't, I won't freak. So this one, how do we name this? Nitrogen monoxide. We don't say mononitrogen monooxide. If it's one element at the beginning, we just say the element name. We only use mono to describe single elements in the second spot. So this is nitrogen monoxide. I'm not writing this all down in other classes. I'm doing it for the video. So you guys are lucky. I'm writing it. All right, the next one. Sulfur what? sulfur trioxide. Next, nitrogen dioxide. Next, tetraphosphorus pentaoxide. Now here's the thing, I have some students, oh, not penta, decaoxide. I have students who want to do something like tetraphosphide or something. No, the first spot is the element name, and then you don't change the ending until you get to the end of the compound, okay? Next one, dinitrogen tetraoxide. And then next, nitrogen trifluoride. Just in the spelling of fluoride, just tell yourself it's not flour. I literally have to tell myself every time I write that word down. It's not baking a cake. You're making an element. All right. This one. Is that a, I can't read this. 3 and a 5. So it's triphosphorus pentaoxide. And then this guy right here. Oh my God, y'all, I'm getting tired. Carbon penta, it's pentanitride. Oh my God. All right, carbon tetrachloride. And that's a common organic substance that's kind of poisonous, but they still use it. All right. We can do these really quick because, well, they're mixed up. So we're going to actually have to figure out if they're ionic or covalent. So silicon dioxide, ionic or covalent? How did you know? Di. It has a prefix in it, so you don't even have to think, right? But however, when we get over here to barium fluoride, barium's a metal, right? Fluoride's a nonmetal. That's an ionic substance. So we have to balance charges. What is this? Barium's +2, fluoride's -1, so it is BaS2. Boron trichloride, ionic or covalent? Covalent, so it's BCl3. Lithium phosphide, ionic or covalent? Ionic. Lithium is a +1, phosphide's a -3, so we get Li3P. Xenon tetrafluoride, ionic or covalent? Covalent, so we get Xe(F4). Tellurium tetraiodide, ionic or covalent? Covalent, Tei4. The rest are all covalent. Phosphorus pentabromide and sulfur dichloride. Okay? So it's going to be up to you now. We're going to do ternary tomorrow. We're going to do the ternary first and then do the quiz. Study before you come to class, because if I'm lecturing tomorrow and you're studying while I'm lecturing, I'm going to not be a nice person. So get your studying done. But if you did your homework and checked it, there's really not a whole heck of a lot of studying to do. But you can come in the morning and ask me questions. I will be here. And if you do not know those polyatomics, bring that sheet to class tomorrow, because I'm going to be calling on people for practice. So if you need that sheet in front of you, bring it. But this is where I'm starting you to expect you to kind of know these polyatomics from your Chem 1 year. Okay? All right, that is all.